Okay, so I was a little surprised that no one asked me for any hints on the homework, and a little distrustful that that meant that everybody has completely mastered all of the homework. So I thought I'd send some hints along um, this time anyway, but in the future, please um, look at the homework enough in advance so you can ask me questions. Anyway, for problem one, I think the two really hard parts of this are this first part, which actually I think is an interesting question and not at all straightforward. And then this part, which is give an example where the inclusion is proper. So let me talk about each of these pieces. So for part one, let me suggest that a contradiction proof would work. I don't know where I got purple from. So a contradiction proof would work. So you want to show that um, U is contained in the closure of A intersect U. And there are some assumptions here. Remember, you have to assume that um, A is dense. So make sure that whatever your proof is, if it's different than mine, that it depends on A being dense. So I've had several people come to me with what they thought were proofs of this first part, and they never used the fact that A was dense. If your proof doesn't use the fact that A is dense in X, then it's not going to be correct because it's actually not true generally for two sets. Um, it's only true if A is open and or if A is dense and U is open. Anyway, my suggestion is contradiction. So we want to show that U is contained in the closure of A intersect U, and I would say suppose not, then there exists an X in U such that X is not an element of the closure of A intersect U. And just to get you started on this, what does it mean? Well, if X is not in the closure of A intersect U, then there exists an open set, um, V open I'll call it, um, such that, well, X is in this open set, and V open, this open set, um, intersected with the closure of, or intersected with, rather, I don't need the closure there, intersected with A intersect U is the null set, right? Because if X were in the closure of A intersect U, then every open set around X would also intersect A intersect U. Um, and then you can show that this implies there's um, another smaller open set, V tilde, open if you like, that's completely contained within U, such that V tilde open intersect A intersect U is equal to the null set. But since V intersect V tilde is a subset of U, then this implies that this is an open set that uh, this is an open set whose intersection with A is the null set. And then you can go on to say, and of course, X is still in V tilde open. So there's an open set that contains X that does not intersect A, but A is supposed to be dense, and so you can get a contradiction for that. Contradiction. For the second part, for this part of the second part of the question, give an example where the inclusion is proper. Um, Consider, I won't give you the whole thing, but consider, this is kind of 2.2, consider um, a sub n equal to, let's say, the set minus 1 over n to 1 over n. And this is in the real numbers with the ordinary topology. And then look at what is the closure of the intersection over all n of a sub n, and, well, n in the natural numbers here. And what is the intersection over all n of the closure of a sub n. I claim they're different, and they show this point. These 3 bits are just untangling the definitions in terms of sets. You can do them in set builder notation or in terms of double containment. So the second part, or the second question, deals with the Cantor set, and it's possible not everyone has seen the Cantor set. So the Cantor middle third set is the interval 0, 1 with a bunch of intervals taken out. And the way we think of it is as a bunch of steps. So C1, which you could think of as Cantor 1, is the interval from 0 to 1. C2 is C1 with the middle third taken out. In other words, the middle third of the interval taken out. C3 has the middle third of C2 taken out. In other words, the middle third of the middle third. Then C4 has the middle third of each of those intervals taken out. And you continue that, and then the limit of that process gives you the Cantor set. In other words, everything that's left over after you've limited out in this process is the Cantor set. The Cantor set has a lot of interesting problems and turns out to be kind of an important problem example in topology. And there are several ways to think about the Cantor set. You can think about it in interval notation. So C1 would be 0, 1, C2 would be 0 to a third and 2/3 to 1. C3 would be 0 to a ninth, 2/9 to a third, union 2/3 to 7/9, union 8/9 to 1. So then you can see how that process works. And notice that the endpoints of each of these intervals always stay in the rest of the set. They never get sort of knocked out of the set. So the endpoints always last. So you know there are some points. The Cantor set is non-empty. Another fact about the Cantor set is if you do it in base 3, in other words, you use base 3 expansions, then the Cantor set is all real numbers, all base 3 real numbers with ternary, that's base 3 expansions that involve only zeros and twos. So for example, the number 0, 2, 0, 2, 0, 0, 2, 0, 0, 0, 0, 0 would be in the Cantor set, and I can tell that because it has the ternary expansion that has only zeros and twos, right? And of course base 3, in base 3 the only numbers you have are 0, 1, 2, and then mod 3 you go back to 0. So that's one way to think about the Cantor set, as all ternary decimal expansions with just zeros and twos. So the question actually asks you to show that it's a perfect set, and my suggestion is to pick an element of the Cantor set and then consider the set of open balls of this form, and that's a 3 there, 1 over 3 to the nth power. And this is a shrinking set of open balls, and this is in a metric space, so we can use the metric, so we're actually looking at open balls. And we can show that it's a limit point in a metric space. Now if you haven't watched my video on limit points in a metric space, you may want to watch it at this point, because this is a metric space and you're showing every point in the Cantor set is a limit point of the Cantor set. So really what you have to do is show that any open ball around C, which is an arbitrary element of the Cantor set, contains at least one other point that's also in the Cantor set. So each point of the Cantor set is a limit point of the Cantor set. The last problem in the homework I'm going to ask you about is about a metrizable space. In other words, a space that we can put a metric on. So, for instance, the real numbers, we know there are several ways to put a metric on the real numbers. So it's a metrizable space. Not every topology has to come about from a metric. We know that. For instance, the 3-point space doesn't have any nice metric at all, as far as I can tell. In fact, I can prove that it doesn't. Let's show that then you're asked to show that a metric space is always Hausdorff and first countable. Now, I didn't actually talk about first countable in class, but the definition is in the book, and I think you can parse the definition. And in fact, in the book, it actually tells you how to do this problem. So this is just a quote from the book. A metric space is first countable by taking the open balls centered at a point with rational radius for the collection ux. In other words, the uxi for every point are going to be the balls around x with rational radius. Or maybe I should say, maybe I should write my rational number as a over b for a and b in the integers. And just a tip that the rationals are a countable set. So if you can show that this is true, if you can show that this meets the definition, that these sets meet the definition that you need for first countable, then you've shown it because the rationals are countable. The other half of this I actually did in class. It's in the notes where I said that a metric space is always Hausdorff, which is basically T2. And I'm just going to remind you of the drawing I had there. Any 2 points, you can find the distance between those 2 points, and you can draw balls around those two that don't intersect. Now I'm going to actually ask you to be a little bit more precise, and I was more precise even in class, and it's available in the notes. But this drawing really captures the entirety of that question. Anyway, if you find this useful, please let me know. If you find it ridiculous,